So first, thank you for letting me presenting it today. I will present you today a project that we made in collaboration with a lot of people, but mainly scientific people. And the aim of this project is to recognize the whole world's flora using deep learning at scale. So first, just a quick words about CNES. So it's a national tier 1 center with 3 national strategic missions. The first mission is high performance computing. So we operate a big machine, which is about 3.5 petaflops. The second mission is long-term digital preservation. So the idea is to be able to keep data for multiple years in our data center and to make sure that, for instance, in 10 years from now, we will still be able to open the data, reuse the data, and maintain its integrity, in fact. And the third mission is to host national computer platforms. For instance, we have all the PhDs in France that are stored in our data center in Montpellier. So CNES is one of the 3 national data centers in France. It's based in Montpellier, so it's pretty close from here. But just to let you know, I went to Amsterdam and then to Milan to come from here, so it's quite a long trip. We also have 2 other national data centers in France, based in Paris, or close to Paris. One is Idris, and the other one is TGCC. And you will have a quick update on Idris later on this afternoon. If you want to have more information about CNES, please feel free to visit the website, or ask me a question after this presentation. So coming back to the challenge that we are facing with the world flora recognition, we know that we have more than 369,000 species of flowering plants in the world. And we want to increase our knowledge on those plants for multiple reasons, for health, about the food crisis, about the biodiversity crisis. So we have to keep our knowledge about this data set and to increase it as much as possible. Nowadays, we have troubles to keep that knowledge. We only have specialists that can analyze the plants, and we have a very rich biodiversity in some region of the world where scientists are not really present, and so it's very difficult to keep all the knowledge of all those species in a human perspective. So the idea was to create a platform, which is a citizen science platform, and the idea is to use machine learning to identify plants. So we have 3 main steps for this platform. We have the data, so biodiversity data at the beginning. With this data, we train our deep learning engine. Then it's used by the users to recognize plants, and then the users say, okay, it's the right plant that you identify using this machine learning engine, and then it increases the data of the biodiversity dataset. So it's a virtuous cycle, and users really help the scientists to increase their knowledge about the biodiversity, about all the species around the world. So how is it working? It's based mainly on a convolutional neural network. I won't really go into details. It's really something which is basically used in deep learning. And we have visual feature extraction at the last layer. And the idea in the end is to define the different classes which represent the different species that we want to recognize. So this is part of the challenge. If you have more than 300,000 classes, in the end, it takes a very long time it takes a lot of memory to store everything. I'll go over that later on. So a few numbers about PlantNet. It has been downloaded more than 8 million times. They have between 60 to 100K users per day. It's available in 11 languages, and at the moment, it can recognize 17K species. So clearly, it's not what we are aiming at. You can see here that the main download country is France. And there is not, in the top 10, there is not Switzerland. So if you want to put Switzerland in the top 10, you can download it now. And what we can see, so with 3.3 million users, we have more than half of them that used the application more than 5 times. So it's a very good number for them because it's very easy to have an application which is downloaded a lot of time, but reused so many times is not the case for all the applications, because we know that when you download an application, if it doesn't work, just trash it. It's okay. So it's increasing, and it's very funny because in summer you have a peak of downloads, and in winter it stops. So it's a standard behavior, I would say, but it's still funny to see it on the graph. So this project is based on an international collaboration with a lot of different entities that are working in this project. And I will just point out that we have a partnership with the Botanical Garden of Geneva in Switzerland. And about the app, to end about the app, 12% of the usage of this app is for professional purposes, and 88% for personal usage. So it's mainly personal usage, but still there is an impact for the industry. About the personal usage, you can think about house plants, identify what you have in your house, in your garden, when you go for hiking or everything. You can even try to, with your tattoo, you can try to identify what is the flower that you tattooed on your feet. So it's a good idea. If you just like the flower that you tattoo, you can have an idea of what kind of flower it was. You can try to trick the app also. You can do whatever you want with the app. You can even post a picture of your holidays and see what it will give you. It's just have to upload a picture. For instance, this morning I went for a quick hike in the park, just behind us. And here you can see I have a picture of a landscape, and it gives me a result which is not totally true, which is completely wrong, in fact. So it tells me that it's daisies in a field. So yes, if you look it for very far, you can imagine that it's daisies in the field. But that's not the right way to use this application. So if you want to really have an added value for using this application, you have to give a clear view of what you want to have. And so if you zoom in on this particular section, you have this, and this is recognized as a tulip, which makes more sense. So about the professional usage, for agriculture it's very interesting because you can recognize the crops, you can recognize the diseases on your plants. It can also help people that are not completely used about their cultures to identify the different crops that are growing and so on. So it's very important for industry in agriculture. For education, it's important as well. You can go for a hike with a school and make them identify plants. It's very interesting to make people aware of what is around them in terms of biodiversity. Yeah, you have a lot of different areas, for instance, tourism. There is a partnership with a zoo, which wanted to have a micro project to identify the plants in the zoo and in the botanic garden. And so you can download the app, and then instead of having different panels everywhere with plant names and so on, you just download the app, you take a picture, and it will tell you what kind of plants you are looking at. It's also used by researchers, so we can do projects such as invasive species distribution models. So if you want to make sure that some species do not invade your whole territory, you can use PlantNet because people are referencing the plant that they are taking picture of, and then you have a map of the invasion of the different plants that you want to eradicate from your region. Of course, it can also help with epidemiology to identify disease and so on. So I'll go a bit more into the technical details. In order to assess this framework and to be able to compare what the deep learning can do versus the human knowledge, there is a challenge every year, which is called Life Clay. And the idea is to give us a data set to researchers and to make them train their model with the data sets. And then we give them a test data set, and then we can compare everything that they have done and have an evaluation of their results and so on. And then we can identify what is the model which performs the best in terms of recognizing the data set that we give to them. So this is the evolution over the years of the size of the data sets. So just at the beginning, we only had 71 species, and now we are using more than 10,000 species. So the evolution is not linear at all. It's more or less exponential, and we have a lot of data, and it's more and more difficult to get better results at what a human can do, in fact, at the beginning. So about the results, what is very interesting on this slide is that here we are using different methods for machine learning and for classifications. And we see that at the beginning, on the 71 species with 5,000 images, we were able to more or less identify 20% of the plants. And we see that using support vector machine and Fisher vectors, we doubled the ratio in 3 years. But with the arrival of machine learning, we have a huge gap. And in fact, the deep learning is really the technology that can give very, very good performances. And in 2017, with 10K species, we achieved a best performance of 0.92. So it's very, very impressive. If we compare it, so this one is for 2018. So there was a new test with a new data set and a new test data set. And for this year, the best machine was better than the 5th best human biologist in the world. So only 4 biologists were better than the 5th best run with the machines. So the machine is not better than the human at the moment, but seeing how it increases here, I don't want to bet, but I'm pretty sure that in a few years, the machine will be number 1, or at least number 2. So this was for what I presented you before. So the idea was to test on 10,000 species. As I told you, PlantNet is currently running with 70K species, but it's clearly not solving the problem, because the problem that I described at the beginning was to recognize the whole world flora. And I told you we have more than 369,000 species in the world, so we are clearly far from what we are aiming at. And in fact, one of the very difficult things for learning the biodiversity at this scale is that we don't have enough information about the plants that we are working with. So here you can see that for maybe 5,000 species, we have more than 100 images per species. And in fact, we know that we have less than 15% of the plants that have less than 10 images. And for 50% of the plants, or more or less 50% of the plants, we only have one image. So it's very difficult to train a neural network with only one image for a plant. And in fact, that is a big issue with training such a neural network. So how did we manage to get the data? We did a big query on Bing and Google with 300K species, and that enables to collect 12 million images for a bit less number of species, and that makes 1.5 terabytes of data. And so those 12 millions are 11 millions of web data plus 350K images from Encyclopedia of Life and 400K images from citizen science data. So those data are coming from PlantNet. So when you make a picture of your plant and you validate that it's the right plant, then it comes into the database. As I told you, it's a highly unbalanced distribution. 50% with one image. If you are aware of AI and deep learning, you know it's very difficult to train when you have so few data on the classes that you want to identify. And you have noise depending on the species. For instance, with Arnica, it's a plant, but it's also a medicine. So when you query on Google, you have a lot of noise, but I'm pretty sure that you all know about that. When you query on Google, you always have weird stuff that are coming up. So to be able to solve this challenge, we had to identify the hardware that we wanted to use. We know that our last layer, because we have a lot of classes, is 300 times larger than the state-of-the-art models. We don't know if we had to distribute or not distribute on the system. Do we have to use CPUs? Do we have to use GPUs? Which network? What is the quality of the model, and so on. So a lot of questions were coming up. And we decided to define a test set. And with this test set, we started to train our neural network on the machines. So as I told you, we had to define which hardware we wanted to use. And in fact, thanks to Gency, which is in France in charge of the national call for tenders, and which is buying the machine and deploying them in the different centers, we discussed with Gency, and they said, okay, you can use the machines to perform your test. So we tried a GPU cluster, which is hosted by Idris. It's an open power platform with 12 nodes, so it's a prototype machine. With 4 GPU per node, which leads us to 48 GPUs, so it's a good candidate, at least at the beginning, for a test case. We are using IBM Power AI framework with Caffe and TensorFlow, or TensorFlow, in fact. The second machine is Irene, which is a CPU cluster hosted by CEA. So here we have much more nodes because it's a production machine. So 1,656 nodes with 2 processor Intel Xeon Platinum processor, 24 cores each. So for those who are not familiar with those numbers, it's Skylake processors. And on this machine, we are using Intel Café plus Intel MLSL. MLSL is a machine learning scalable library, which is also delivered by Intel. A third machine was used on the preparatory phase. It's an Oxygen machine. It's more than 3,000 nodes, Intel Xeon processors. We also use Frioul, which is a Xeon Phi platform, and still with Intel MLSL plus Intel Café. For running those experiments, we had quite a huge team. People from South Sahara, people from PlantNet, myself, and engineers from Intel. So a lot of variety. People from South Sahara are very familiar with deep learning at scale. So it was very interesting to have them in this project. So we had some difficulties with Intel. It's just basic features. In fact, we couldn't use Learn as it was configured on the machine because it requires a passwordless SSH for initializing the connection, so we just passed through that. And we also had an issue with the protobuf library. It's limited to 2 GB files, and it was impossible to serialize the ResNet 50 model with so many classes. So I told you before, we have a very large amount of classes, and we had to use a dimensionality reduction trick. But I'm pretty sure this will be solved in the near future because protobuf is developed by Google, and I'm pretty sure that if Google could recognize billions of different classes, they would be very happy to be able to identify each person on the planet with a different class. So it will probably go up to way more than 2 GB. So I presented you the machines. The first experiments were carried out on Wesson. So the GPU machine, we have a top 1 accuracy of 0.35, top 5 0.45, and it takes 6 hours per epoch. So it was quite okay, but if you want to run, like here, 50 epochs, it leads you to 300 hours for a single run. And if you want to compare multiple runs to get the best model that you want for your data, then it takes multiple weeks and so on. So it was not, this target could not be used. On top of that, we had trouble to use multiple nodes for the same simulation. So we moved to, that's why we moved to the CPU architecture, and we ran the test on the CPU platform. So we tried on Oxygen, which was a Broadwell-based architecture. I didn't report the numbers here because it was more as a proof of concept that the Intel libraries could be run on a CPU machine and could scale. And in the end, we managed to run on the Irene with 512 nodes, 50 epochs, in 10 hours with 12 news per epoch. So it was way more efficient. But of course, here we are using 4 GPUs versus 512 nodes. So it has to be more efficient. What you also have to know is that here we are working on a fine-tuned model. So that means we are using a pre-trained model and we are only fine-tuning it to make it aware of plants, in fact. Here we are running from scratch. So that means we are running a model which does not know anything, and we only train it using the plant data. And this is why we have a better accuracy, in fact. So the big challenge here was to see if, from scratch, we have a better accuracy than what we could have using a fine-tuned version of a network? And so the answer is yes. Just a few words about the scalability. So the idea was to push the model on as many nodes as possible, and we have seen that we can go up to 1,000 nodes with about 80% of scaling efficiency, which is quite good. If we want to move up to 1,300 nodes, which was the hard limit that we had for this experiment, we have a very less efficient version of it. The main issue here is that if you want to use way more cores, way more nodes, using Intel MLSL and Intel Café, in fact, with MLSL, you have to create communication servers, which will help you to handle all those all reduce and so on that you have, and which leads you to very bad performances training neural network at scale. And using more than 1,000 nodes makes you use even more servers for communication, and then you have even less code that are working, and that's why we have a very bad, not very bad, but a bad scaling efficiency compared to what we can have using 1,000 nodes. But still, for this kind of training, you can train at scale a neural network with about 50,000 cores. With Intel MLSL and Intel Café, it's not an issue, and you will get very, very decent performances. So, the conclusion on this study is that you have seen we have 37.5% of accuracy, and so it's an improvement because we had only 35% before this experiment. But still, we know that the main problem on this challenge is that with 50% of the species, we only have one image, and that is clearly the reason why we don't get very, very good results on this model. We can use state-of-the-art CNN with 300 K classes. It's not an issue. We only had to use a reduction trick on the protobuf, but it's okay. And we have been able to use hundreds of nodes, even thousands of nodes. But it's still very difficult for the research team to use that. So we were here to help them because we are HPC experts. We can support them, but without our help, it's very difficult for them to use that. So we hope that maybe in the near future we'll be able to have a very friendly, user-friendly interface which could enable them to run their application on multiple nodes, thousands of nodes, and have very good performances and good scalability. About the perspectives, we wish that we could include the big one, which is the big challenge, in the PlantNet platform, and then being able to tell to the people that they can recognize up to 300,000 plants, and then we hope that people will be able to contribute even more, and maybe resolve this issue of 50% of species with only one image. So it's clearly not easy because people have to be more or less plant experts to make sure that the image that they're uploading is correct. But currently it's the only way to reach that goal, and so we hope that in the future people will continue using this application, upload the data, increase the database, and make it more and more accurate. So just last words. We were very proud of this project because it involved all the partners in France that we have. So the scientific people are working at INRIA, We worked with Idris, we worked with CNES, we worked with TGCC, so CEA, and it clearly helped the researchers to get used to the HPC facilities, and we are trying to push people to HPC with AI, and we'll try to continue to find some projects, such projects that needs very important HPC capacities, and to enable them to solve their challenges. And thank you to all of them and to you that were there for listening to this presentation.